Okay, so here's the solutions mini unit real quickly. Solutions are something you guys are probably familiar with. Anything that is a homogeneous mixture is considered a solution. So, by definition, um, things, mixtures that are homogeneous, this uniform composition throughout, that is a homogeneous mixture. They're composed of two parts. Solutions composed of a solute, which is the part that's being dissolved, and the solvent. The solvent is the stuff that's doing the dissolving. So if we consider something like salt water, all right, salt water, we have sodium chloride, we have the salt, which is the solute, we have the water, which is the solvent. Together, they make the solution. Okay? So copy those notes down, pause this, come back. Now, to dissolve is a term that you guys, I'm sure, are familiar with. But if I were to ask you to define that, you'd be like, well, I don't know what that means. Well, dissolving has to do with interaction between the molecules, the intermolecular forces of attraction. The whole idea of polarities, different substances, polarities interacting. So the term, the phrase likes dissolve likes is used frequently when we're talking about dissolving. So polar solute is soluble in a polar solvent. Similarly, nonpolar solutes are dissoluble in nonpolar solvents. Lots of examples for those. Examples include um, when you have salt and water. So here's an example of salt water. The water molecule is a polar molecule. You have a negative end, which is the oxygen. You have a positive end, which is the hydrogens. All right. So this negative end of the water molecule is attracted to the positive sodium ions. Oppositely or conversely, the positive ends of the water molecule are attracted to the negative chloride ions. So sodium ions are attracted to the oxygen end, which is electronegative, more electronegative than hydrogen. And the chloride ions, which are negative, are attracted to the less electronegative end, which is the hydrogens. And that's how salt dissolves. Salt molecules, salt particles, they dissociate. And when they dissociate, they separate into two different parts. Table G is used a lot in solubility and solvents and solutions. All right, so table G um, talks to you about it's basically just telling you what different substances are. So if you look at table G, let me change this so you can see the whole page. All right, so table G shows us a bunch of curves, 10 different substances, their curves. And if substance is on the line, if it's on the line, that means you have a saturated solution. The term saturated means the solvent is holding as much solute as it can. That's what saturated means. The solute is holding as much solvent as it can. That is saturated. As you can see, the saturated line, the solubility, changes depending upon the temperature. Table G is all out of 100 grams, right? So out of 100 grams, these are your different solubilities. Ionic substances, solids, their solubility increases as the temperature goes up. Then there's these three that are going down. Those three that are going down, those are um, those are gases. Gases solubility, they decrease as the temperature increases. Right? You guys know that because if you had a hot soda versus a cold soda, which one's going to be fizzy? Well, the cold soda will be because um, the carbon dioxide gas is more soluble in the cold solution solvent than it would be in a hot solvent. Solutions are measured, the concentrations, their solutions are talked about in terms of concentrations. Concentrations are measured either using moles of liter per solvent, which is called molarity, and both of these are found on table T, or concentration, how much stuff is in it, is measured in parts per million. Parts per million you've probably heard of. That's the grams of this divided by the grams of that times 1 million. That's how you get the parts per million. Molarity is a more common term for chemists. Molarity is the moles of solute per liters of solution. Remember, that's liters of solution. Up here, we're talking about grams of solution. Down here, we're talking about liters of solution. and molarity is abbreviated with a capital M. So we would be doing a molarity of glucose in soda pop lab. If you have a scale, if you missed this and have a scale at home, a kitchen scale, you can do this. I will put this on the website, but it's basically figuring out how much glucose there is in a sample of soda. So we can talk about that later. There's a couple other terms here with solutions. Term miscible and immiscible. Miscible just means liquids dissolving in one another. If it's miscible, without the IM, if it's miscible, that means the two liquids do dissolve in one another. If it's immiscible, that means they do not dissolve in one another. I like to think of this as, you can use the idea of mixable. Sounds like miscible, sounds like mixable and miscible. See how? All right. Down here, we talked about the three different types of solutions. We can either have a saturated solution, an unsaturated solution, and a supersaturated solution. Saturated solution is on the line because it tells you the maximum amount of solute is in that solvent at that temperature. The one way they tell you typically is they say, hey, there's some undissolved solute on the bottom of that solution. That just means you stirred as much as you could and no more will dissolve. That means it's saturated. If you have an unsaturated solution, well, that just means it's holding less than it could amount. And the term supersaturated is a weird idea. Happens not all the time, but sometimes. A supersaturated solution means more solute is dissolved in that solvent than should be possible. And this happens in only a few different circumstances. It's a very unstable solution, which means it would come out of solution quickly. Instant hot packs change into that. So those are the different solutions. Brings us back to table G, talking about table G. And then there's table F. It's pretty self-explanatory. There's table F. Table F is tough. Table F is tough because it talks about things in terms of solubility, and then it gives you exceptions, and there's two sides. So you have the left side here. So if you're looking at your table F in your reference tables, it shows you all these things here, and I'm just going to scroll down a little bit. All of those ions form soluble compounds in solution, in aqueous solutions. So if it's a group 1 ion, it doesn't matter what it's attached to. If it's lithium something, sodium something, whatever it is, and you'll see here there are no exceptions, it's always going to be a soluble compound. So lithium, and then choose your anion. Lithium chloride, lithium sulfate, lithium carbonate, lithium, whatever it is, lithium, any of the group 1 ions, they're all going to be soluble. The same is true for ammonium compounds. All the ammonium compounds are going to be soluble as well. Now, those two are cations. The next bunch are all the anions. So if you have a nitrate, any kind of nitrate, if it's something nitrate, it's going to be soluble. Doesn't matter what the first metal is, whatever the cation is, it's going to be soluble. Same is true for acetates, and for the most part in hydrogen carbonates and chlorates. All right. The next ones, none of these have exceptions. They're always soluble. Now, the next ones here are the halides. Almost every single halide, it's like sodium chloride, for example. That's a halide. Sodium fluoride, potassium iodide. Those are all soluble. The only exceptions are 3 exceptions: silver, lead 2, or mercury 1. I know you're saying, wait, that's mercury 2. No, it's 2 mercury atoms that are together are plus 2. It's called mercury 1 or dimercury. That one, and sulfates. Sulfates are almost always soluble, except under certain circumstances. So with silver, lead, again, you have silver and lead just like in the halides, but then you also have some group 2 metals, calcium, strontium, and barium. Those guys are all going to be insoluble, okay? But otherwise, any group 1, ammonium, a nitrate, an acetate, a hydrogen carbonate, a chlorate, they're always going to be soluble. Okay, so that's this side, the left side, the ions that form soluble compounds. The other side is the ions that form insoluble compounds, things that don't dissolve. Well, generally, carbon. This is why this is weird. This side makes it tough. This side says, all right, these things don't dissolve. Carbonates are insoluble, except with group 1 or ammoniums. So almost all carbonates are insoluble, except like lithium carbonate or sodium carbonate, potassium carbonate, or ammonium carbonate. Then the exception to the insolubility means they're soluble. So it's kind of like a double negative, which is confusing. So carbonates are insoluble, except with these guys. Chromates are insoluble, except with group 1s and ammonium and calcium and magnesium. And the same is true for all of these. Then you have phosphates. They're insoluble, except with the group 1s and ammonium. Sulfides, the same. Hydroxides, you can also throw some group 2s in there. So calcium hydroxide, barium hydroxide, strontium hydroxide, they are exceptions to being insoluble, meaning they are soluble. That is why this table is so difficult to understand. All right. So the first side, compounds that form soluble ions that form compounds, and then the second side are the insoluble ones. All right. I'm going to put up on the web page. I'm going to do this worksheet here, worksheet of solubility. So you want to go through here and check these out. So let's do a couple of them together. So aluminum sulfate here. So here's table F, aluminum sulfate. So you'd look for the cation aluminum. Well, aluminum's not talked about anywhere here, but sulfates are. And it says right here that sulfates, let me scroll down a little bit. Scroll down. It says sulfates, they are soluble except with calcium, strontium, barium, or lead, or silver. Well, aluminum is not one of those. So therefore, aluminum sulfate is soluble. See how that works? The second one, potassium chromate. Well, I'm going to stop right there with potassium because I know potassium is a group 1 metal, and group 1 metals are always soluble. So that one too is going to be a soluble. So those two would both get a soluble notation. Go through this, check against table F, and see. So go through, when I say this, I mean the solubility worksheet. Go through that, check against table F. Make sure you have table F open with you while you're doing this. And then after that, check back. Okay? Hopefully you checked through that first time, did that on the quiz. Now you can get this part here, this double replacement reactions. Now, it says complete and balance the double replacement reactions. Remember that whether it's going to be a soluble or insoluble. The only reason these things happen is because they form an insoluble precipitate or they form a gas. So this one here, if it's a double replacement reaction, you know the two cations are going to essentially switch partners. And when they do, they're going to form two new compounds. To do this, you're going to get potassium with nitrate, potassium nitrate, and you're going to get magnesium with carbonate. Magnesium carbonate. So now you say, okay, is this reaction actually going to happen? Is this reaction going to happen? Does it create an insoluble precipitate? So what you do is you look on table F and you say, all right, well, what's going to happen? Well, right here I can see automatically precipitates, potassium, they are always soluble, as are nitrates. So that's going to be an aqueous solution. All right. Magnesium carbonate, well, is that going to be an aqueous solution? Well, we have to look and find out, oh, wait a minute, carbonates, they are insoluble almost all the time, except with group 1s and alkali group 1s and ammonium. Magnesium is not one of those, so that's going to form a soluble precipitate. So this reaction will proceed. So if they were both aqueous, then you would say, okay, this is not a reaction that's going to happen. This reaction would just be two liquids in solution and nothing's going to happen. But this one, because magnesium carbonate forms an insoluble precipitate, this one will occur. So while you're working on the worksheet, you can go through this as well. More of the same.